Hello everyone. We'll wait for maybe 2 more minutes and then we'll start the session. If anyone wants to join. Today we'll be discussing week 7 content, which covered recurrent neural networks and their use in vision models, recurrent neural networks introduction, backpropagation in RNNs, LSTM, GRUs, and video understanding using CNNs and RNNs. So we'll go through a standard code walkthrough for recurrent neural networks and LSTM and gated recurrent units. Hopefully, this will be helpful for you to understand how sequence to sequence models work or sequential networks work, like neural networks. So I'll wait for 5 more minutes for people to join and then I will start the session. I'm muting myself now. Okay, so I don't know if anyone is joining, so I will start. So recurrent neural networks are basic the models which we use to neural network based models which we use to model sequences or time series data. Uh, these are some import statements: import torch, import from torch, import NN, and import numpy as NP. So suppose you have a text, hey, how are you? Good, I am fine. Have a nice day. So and we want to model maybe the next sentence generated after this, or what will come after this particular have a nice day, what will be the next sentence or next word, or overall structure, like sentiment of this particular sentence or set of sentences. So suppose what we do initially is, because neural networks only can't process the textual data. Here we have a textual data. So what we do is we join all the sentences together, extract the unique characters from combined sentences, create a dictionary that maps integers to the characters, and create another dictionary that maps characters to integers. So we have int to character, character to int. Here for this particular code walkthrough, we'll be doing a character level modeling instead of a word level modeling. So if you look at the character level modeling, basically you can think of it as, suppose English language, then we have 26 characters, and we want to predict what comes after H, what comes after E, what comes after Y, what comes after H, O, like that. So uh, you can look at this, the character to int dictionary maps each character in your sentence or the corpus to a index, like 0, I is mapped to 0, A is mapped to 1, H is mapped to 2, and into character is a reverse mapping where it maps the index 0 or integer 0 to a character I. So, so now we want to know what is the maximum length of the any character, any word in this particular data or text. So suppose here 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, right? So you can see that this is a 15 length character length sentence, and same way we can calculate the maximum characters occurring in this, like the character length in this sentence and character length in this sentence. What you will get is the longest string has 15 characters. So now, because we have to treat it as a tensor, uh, we cannot have each sentence of a different length. So what we will do is we will do a sort of padding, what it will do is it will add a white space until the length of all the sentences matches in your particular batch or in the whole corpus. uh, okay, so now padding simply means we want to make all the sentences of all the uh, all the strings are of same length. We want to make sure so that we can process them in batches, else we have to process them one by one, one string at a time. Okay, so now we want to create list that will hold our input and target sequence. So if I want to ask you what will be your target sequence, for a suppose you want to generate the next sentences and you are given this particular text data, this is your input text data, what will be your target sequence? So you can think of it as, you can treat this whole data as like one character as your input at a time. You can treat one character as an input and rest of it as a next character. So suppose input is H, E is your next character, input is HE, your next character is Y. Same way you can do it. And basically you can see here, suppose your input sentence is, hey, how are you, your target sequence will be next, like taking the next character from your sequence and moving it to the next character in the target sequence. So we just shift it by one whole string. So you start in the target sequence, you start with E and end with that U of UY, YOU. Same way you can have another input sequence where good, I am fine, and your target sequence is OOD, I am fine. So basically you'll treat it like in auto regressive manner, where given one character, what is your next character, given two characters, what is your next character, given three characters, what is your next character. So suppose here we have 3, 6, 7, 8, 11, 12, 13. So given all this, he, how, or, why, who, what will be my next character, which will be you here. Okay, so this we have created this list that will hold input sequence list and target sequence list. Uh, Input sequence simply have the last character removed from it, and target sequence has first character removed from it. Now neural networks can't treat your model, can't take your this thing words as or characters as input, so we have to convert them into indexes. So here we simply do that for I in range length of text. Each character is converted to an integer for input sequence and target sequence, right? And for our model, we convert each of that index into a one hot encoding vector. So suppose you have total 26 characters in your data. So then you will have a 26 dimensional vector, 0 1 vector, 26 dimensional 0 1 vector with the corresponding index corresponding to that particular character being 1 and everywhere else 0. So we'll replace the 0 at the relevant character index with a 1 to represent that character. That is your one hot encoding. Okay. So now you have a input sequence which is of size. Suppose you have some batch, multiple sequence in your batch. Each of them is each of the sequence is of certain length, and each of that is one hot encoding size. So sequence length is, suppose your particular sequence has some 15 characters. That is your sequence length, and each character is represented by a say 26 dimensional one hot vector. So your input size is batch size, sequence length, and whatever is your one hot encoding size. So here we have 3 is your batch size, 14 is your sequence length, and 17 is your on hot encoding size. 17 because we have taken the characters or based on the given text. Okay. So now, till now we have a NumPy array of the one hot encoding. Like input sequences are in form of list or one hot num uh, 3D array, like a 3D array here, and same way for target sequence. So we convert them into a tensor. PyTorch tensor. Here we'll be using a PyTorch library to model RNN. So again, then we look at if CUDA is available. This is standard if you want to run on a GPU or CPU. So you look if you have a GPU available, and then if GPU is available, you make sure your device is CUDA, and if your GPU is not available, you make sure your device is CPU. So here the RNN model is defined as follows. We have some hidden dimension and number of layers. We use a neural network module in PyTorch to define a recurrent neural network. We pass input size, the hidden dimensions, and the number of layers we want. And we also specify whether in our data or in our input sequences, whether batch is first dimension or last dimension. And finally, we have a fully connected layer to predict the next character. And in the forward propagation of this particular model, we, because it's a recurrent neural network, so you have something, some, 1 second, give me 1 second. So, yeah. So you have something like this, right? You have a input sequence, you have input here, then you have a recurrent connection which takes in a hidden, and then you have a output O. Okay. So okay, let me write it properly. Give me 1 second. So you have this, right? This is your hidden, and this is your I as an input, and output is your O. So you can see here We have to initialize the hidden state for the first input. For the first input, then we pass the input, which is x here, and the hidden to our RNN object, which returns output and hidden. Whatever number of layers it will process for all the hidden states and return the final hidden state. And then we get the output, then which we have to reshape to feed it into a fully connected layer. And then we use the fully connected layer to predict the uh, basically we'll have a fully connected layer here, which will predict the or whatever is the next sentence. So given uh, up to, like, say input is up to certain length, say 3 or 4 or 5, I will predict the sixth character or seventh character, like that. Okay. uh, so this was a brief overview of RNN, and that is how your this thing will forward propagation will happen. And we can define our initial hidden state to be zero tensor, which is of shape based on number of layers. It will be of size hidden times hidden. Okay. Then here we instantiate the model. We create a object of our model class. We define the model hyperparameters in of epochs, the learning rate. The criterion here is also cross entropy loss, because we are training the model to predict the next token, which we have available as something true token is available, and here we'll be using the Adam optimizer with corresponding learning rate. So in the in the training run, for each epoch, we because we have a very small data, we can pass the whole thing as the input sequence to the model, and then we get the output, and we calculate the uh, loss, cross entropy loss between the output and the target sequence. We backpropagate it to compute the gradients, and we use optimizer.step to update the parameters. And that whole process we repeat a certain number of epochs. Here we have 100, and you can see here that the loss is going starting from 2.4298 going up to some 0.1342, which is our goal. We want to make loss as small as possible. To predict a character, what we do is we take a character, we do the one hot encoding, we pass it through the model, and we take whatever output we get from the model, we calculate the probability of that output, and whichever character in our vocabulary has the highest probability, that will be returned as a output character. Same way we can do the sampling also, using the predict function I defined above. So say suppose we want to sample uh, next 15 characters, and our input is good, and we have trained a model. So you can see that model is able to repeat whatever was given as an output input. You can see that our input characters will have some string like after good. After good it was I am fine, and the model is able to predict that. So it is actually able to mimic the input sequence which we had trained on. So now let's move on to LSTM and GRUs. Here we will be doing a time series time series prediction. So suppose you have some hourly data for some AEP reading. For suppose it's at 31/12/2004. Every hour it starts at 1 a.m. and every hour you have some data. So again you do that. You process the data hourly or weekly or monthly or yearly data, and you create a tensor data set and then data loader object using your training data. Then you check whether you have a I think time series data is almost clear. I don't have to, like, you have just have hourly data, and you want to train us model to mimic this or predict the next step in your time series. Okay, so here we are using a GRU. GRU is also based on your recurrent neural networks, but it has certain gates. One second. Yeah, GRU has only update and reset gate, whereas your LSTM has your forget gate, output gate, and update gate. So GRU actually reduces the number of gates to from three to two. You have input gate, forget gate, and output gate. GRU only has update gate and reset gate. So here also we are using a here also we are using a neural network module to define your gated recurrent unit. Again, we have a linear layer to take the output from GRU unit and uh, predict the next characters. Uh, everything else is same, and similarly you can use the neural network to define a LSTM also. Here we are defining the whole LSTM model using the neural network model. If you want, you can also do it from scratch, but then you have to define the gates in both the gated recurrent unit and LSTM, long short term memory, long short term memory network, right? Uh, then the forward propagation is same in both. As is in recurrent neural network, you pass your input sequence through a gated recurrent unit. You get output, you get hidden state, and you do the recurrent processing till you get the final output. Okay. So again, the training is here we have a function which takes in a model type as argument, and if you define it as GRU or LSTM, based on that it will do the forward propagation through gated recurrent unit or LSTM unit. Because this is a time series prediction, our criterion is a MSC loss. We are again using a Adam optimizer. Forward propagation is very simple. You take your input sequence, you pass it through your model along with your initial hidden state, and you get your output from the final hidden state. Then you calculate the loss, then you do the loss dot backward to compute the gradients, and then you do the optimizer dot step to update the parameters, and the whole thing you will repeat for a certain number of epochs. And then you have a evaluate function where you compare your output sequence with your input sequence. So here you can see that when we train a GRU model, uh, our average loss after the first epoch is very small, and as we train it for more and more number of steps, it goes even further closer to zero. And you can see that when we evaluate the SMAPE, the the mean absolute prediction error goes to very, like, it goes to some 0.3%, which is very small. And I don't have a output prediction but plot for this, but you can also plot and check how good your model mimics the mimics the this thing, your time series data. And let me run the LSTM model also for you to show how good or bad it works. So let's see, it's running, how good it is as compared to your GRU model. Obviously your LSTM model has more parameters, so GRU becomes little more parameter efficient, and LSTM and GRU performance is not that much different. We will see how different the LSTM model performance is, and GRU is actually beneficial for the model here for this particular problem. So let's see. So Good, I am fine. You can see I have run it works pretty fine. We're creating the data now. Pre-processing the data. Because it's a linear regression problem, we might have to do some pre-processing like scaling, normalization. Those things we have to do. So I'm waiting for it to run. So, okay, still running. Save. Okay, this has run. Then we define our GRU class and LSTM class. We also have a train model. Then we train GRU model here. So let's see. It will take some time to train, but let's wait here and see how the training happens. You can see that after 200 steps in the epoch 1, which has 850 steps, the average loss is already 0.006 because this is a very strong model. The number of layers we have taken, uh, we have a hidden dimension 256 and the number of layers are 2. So this is a very strong model for the kind of data we have here. It's a very simple data. Okay, I'm running it for 3 epochs. It takes 2 minutes to run for one epoch. I'm waiting for it to finish. Then we'll run the LSTM model. We'll see the output and compare it with our GRU model. Okay, sweet. You can see that the curve is going down and the loss is actually decreasing from one step to like every 200 step the loss is actually decreasing. Still waiting for it to finish. Okay, so we are done with two epochs. Now the third epoch will run, and you can see the loss has almost reduced by 10 times. So it was 001 here after first epoch. Now it is 0002. So it is reduced almost by 10, 1 by 10. This is a MSC loss. Let's see. Yeah. Epoch third has started. Loss is still decreasing. It has slowed down as compared to the previous one, but previous epochs, but it is still decreasing. I will just uncomment the Listium model. Let's see. I haven't run this, so let me see what happens if I run a Listium model. Okay, half of third epoch is complete. Only one more minute, maybe. Okay, last 200 steps. Then we'll run the evaluation on our test data using our GRU model, which we had trained just now. I'll just run it. I'll simply copy this. And okay. So let me just put this here. LSTM outputs, targets, LSTM SNEP, LSTM model, test X, right? So we define our LSTM model. Okay, this was not. I will just do this. Let's see how much time it will take. It will take more time than GRU model because the number of parameters are more. Even bigger model than GRU model, and you have multiple like three gates: input, for gate, and output gate. Now even 200 steps have not completed yet. Waiting. Yeah. So you can see it's starts with a higher loss after 200 steps if we compare. GRU was at much lower, like almost 10 times of this. But let's see, wait for it to run for three epochs and see how much did we gain anything by running a Listium model or not in terms of this mean absolute error. Mean absolute percentage error. The metric mean absolute percentage error. Right? So you can see it's taking more time than the GRU model, even though the loss is almost same, but it takes much more time than because obviously number of parameters are more, but there's no difference in or very small difference in the average loss at any step. So now uh, I will you can play around with this. I will stop this LSTM model because it will take at least 10-15 minutes. There's no point in, but I can show you. Okay, let me run it for one epoch then because I want to show you the epochs I can put. So epochs I can put here. Put one epoch here. Let's see. Let me finish this, and because I stopped it in between, so my train function hasn't returned anything. That is why I got this error. I'll just run it. Take 3 minutes to finish. Half of the steps are almost half of the steps are complete. How much? So 1 minute 35 seconds. So should be able to finish in 3 minutes some seconds. Let's see about okay, almost complete. 50 more steps. So see about to get complete. 3 minutes. Complete. So it took 171 seconds as compared to 130 seconds for in a GRU model. I'm getting some CODA error because LSTM model, but you can play around with it. You can reduce the batch size. You can uh, do a lot of things here. Finally, you'll get some output, and you can compare it with a GRU model. Uh, Colab has some uh, inbuilt GRU issue and inbuilt GPU issues. That's fine. This was it for the code walkthrough for GRU, LSTM, and RNN models. If you get any doubts regarding this, please ask in our Discourse forum, or you can ask in GSpace also. Uh, I have this much for today. If you have any doubts, please post it in the Discourse forum. Now I'll stop the recording and we can end the session. Okay. I hope you are able to gain something from this. And stop. Thanks anyone who has joined through the live streaming. So I'll stop the streaming now.